Okay, couple of things about your test. If it lets me. There we go. I need to erase. There we go. Okay, so most of you got number one. Basically, you had to use the initial velocity, the final velocity, and then the time to get your acceleration. Basically, you had to use VF is equal to VI plus A delta T twice. First to get your acceleration, and the second time to get the final velocity. That one was okay. The second one, I think most of you got it, but a few of you didn't realize that it asked for, or I can't remember. It needed distance and displacement, so you had to do both. Other than that, everyone seemed to do that correctly. The graph, everybody did fine. That's not important. Okay, this one. This is where you got +1 from. Is because no one got this, which means that I guess wasn't clear about this. Okay, so this object right here, this is your position versus time. So the slope right here is like this, and then the slope at this point is like this, and the slope at this point is like this, and the slope at this point is like this. What you're seeing here is the slope is decreasing with time. If the slope is decreasing versus time, then this object is slowing down. So that's one way of slowing down. If it were speeding up, it would look like this, where the slope would be increasing with time. So, a lot of people missed that. The rest were okay. Okay, this one's always been troublesome. I think a lot of you got the first part, but then it says how far away. Basically, you need to use delta x is equal to vi delta t. But let's say the distance they drive is the same because, Peter Pumpernickel catches up to, Betty Bedbreaker in this case. I think I called it Bed Breakfast. And I don't know, changed the names up. But in this case, there's a time differential. So basically, you would have the velocity of Betty times the time differential that Betty has, and then that's equal to, because that's delta x, by the way, and that's equal to the velocity of Peter Pumpernickel. But Peter Pumpernickel is going to have less time because he left 7 minutes later. So it'll be my t minus 7 minutes, and as you know, that minutes needs to go into hours. And then you can use that, and once again, this is also delta x, this whole thing right here. And so once you do that, you can use it to solve for time and then distance, and you got all your information, and then the rest should all fall out. A number 8, different ways you can do this. Personally, I would have changed 20 miles an hour per second into meters a second, but you don't have to. But basically, what you are doing is you're using VF is equal to VI plus A delta T. And then on part B, once you get that information, you can use delta X is equal to VI delta T plus 1/2 of A delta T squared. Sounds a lot easier than when you're actually doing it, I'm fully aware, but that is all you do. This is from a movie called The Gods Must Be Crazy. It's kind of funny and hilarious. It's from the 80s, but if you didn't know, that's what it's about. And the movie, they actually do throw a Coke bottle into the air because the Coke bottle kind of destroys their tribe. It's a pretty good movie. But anyways, so it says it reaches the highest point in the trajectory at 5 seconds. So if you throw an object up in the air and it comes to a stop at the highest point in the trajectory, you know the final velocity is going to be 0, and that the time it took to get up is 5 seconds, and coincidentally the time to go down is 5 seconds as well. And you can use VF is equal to VI plus actually, no. That you could use later. Oh. Yeah, that is what you do. You gotta get the initial velocities first. Alright, so VF is equal to VI plus A delta T. You know that your acceleration is negative 9.8, and the final velocity is 0. You use this to get your initial velocity. Then to get the height, different ways, but I would just use delta x is equal to vi delta t plus 1/2 a delta t squared. B, that's for A. For B, you use VF is equal to VI plus A delta T. And then to get the height at 8 seconds, easiest way is to use delta X is equal to VI delta T plus 1/2 A delta T squared. Not the only way of doing this, but it's the easiest. And then you're going to plug in for actual 7 seconds. So, that's about it for the test. I do drop your lowest test grade. This tends to be your lowest test grade, so keep that in mind. You will have one more test before the final. You will have questions like these on the final, probably not as hard as number 9. Because, in a normal test, I'll give you one that's a little bit beyond maybe what you've talked about, but not usually on the final. But you can expect problems more like maybe the Big Lots problem or distance and displacement and things like that. Whenever you pass an electric current through a wire, as I said earlier, there is a voltage drop across the wire and electric energy is converted to heat. And this is where I say IV. What is I? I is your amps. And that's actually measured as an A, or a coulomb per second, as I showed you earlier, for those who are astute at their physics 2. And your volts are V, and we measure that in volts. And so when we multiply those two together, like I said earlier, we get power. And delta E is the amount of energy converted from one form to another. So if I go back up here, we're taking electrical energy and we're converting it into thermal energy, otherwise passing off as the flow of thermal energy as heat. Delta T is the duration of which the conversion takes place, as I mentioned earlier. I is the current, V is the voltage, and so your real equation right here is IV delta T. So that's your amps times your voltage times however long you ran your power supply. So, anywho, it's a really handy way of actually figuring out how much energy you put in the system, and for heat and temperature, I really like it. It does have some drawbacks. When you run an electric current through water, it's generally not the you don't want to drink the water while it's doing that. Yeah, it's definitely pretty. And 12 amps, 10 amps, I'm sorry, is a lot. So there is some caution in it, but as long as people are safe, it doesn't really cause any issue. And no one's killed themselves yet, so I'll take that as a plus. So yeah, at least not with respect to this. First set of experiments. From your graphs, you see that for an object, in this case 100 grams of water, there should be a linear relationship between energy and added temperature. The slope of this line means something, and it's called heat capacity. And so when you have this little line here, this is energy versus temperature, and I'm going to draw the best line you've ever seen today. And you notice that your units for heat capacity is going to be a joule per degree Celsius. Heat capacity tells you how much energy you need of a certain amount of massive substance, how much energy you need to move it up or down 1 degree Celsius. This is heat capacity. Most books will call it a K. I believe, it's stretching my brain. Sometimes you'll see it as a capital C in certain chemistry books. I call it a K. Why do I call it a K? Because as we'll get into later, there's specific heat capacity and regular heat capacity. And if they're both C's, that looks kind of funny, especially if one's capital and one's not, because then you're going to get them confused. So I switched a long time ago to a K, and well, no one's complained, so we're going to go with that. So what about for 100 grams of water? Well, the slope of the graph shows that for 100 grams of water, it's 418 joules degrees Celsius. That means you need 418 joules of energy that need to be added to move 100 grams of water to change its temperature by 1, either up if you want to put it in, the energy in, or down if you want to take the energy away. And so when you found that slope, whoopsie, you'll see that it's 418. Analyzing graphs, and I better have fixed this. Notice that even though the mass of the water is increased in each experiment, the data still has a linear relationship. So you should get very similar values, 209, 313, 418, etc., etc. For each mass is going to have a different heat capacity. So note that each mass has its own unique
has, write the word has, there you go. It is, oh wow, English for me, English. Its own heat capacity, there we go. So each one has its own capacity, and every mass will have its own individual heat capacity. How is that useful? Well, it is a quick and dirty way sometimes if you don't actually know the specific heat of the material. But if you do, as we'll get in earlier, it's kind of not as well used, I think. Um, from our data, we see that as mass increases, then the heat capacity does as well. And we can find a relationship between the heat capacity and mass. And that's called the specific heat, as I mentioned earlier. This is actually called the specific heat capacity. I will simply call it the specific heat. And why is that? Because normally, if we're in a lab, and sometimes we would do back and forth between heat capacity and specific heat capacity. If I tell you specific heat capacity, and it's happened before, you might not hear the specific heat or the specific part in front of the heat, and you just hear heat capacity, since 2 out of the 3 words are exactly the same. So instead, I just simply call it specific heat, and then heat capacity. Only one word is used in between the two. It causes a lot less confusion. If you end up teaching some sort of chemistry or physics, and you have to do this, and I have, just call one heat capacity and the other one specific heat. It'll make your life easier. A little life lesson there. So the slope of the heat capacity versus temperature is going to yield the specific heat. So basically what we did was we took all of our heat capacities, and I spelled it correctly, there I go, and we graphed them on the y-axis versus the actual mass, and then when we found the slope, we got 4.18. This is what's called the specific heat of water. It takes 4.18 joules for to heat up 1 gram of water 1 degree Celsius. The unique thing about specific heat is it's true for all of the substance. So this is true for all water. Now you're saying, well, what if the water has, different properties? It's heavier water or lighter water. I don't know. It has more minerals in it or something. Yeah, I mean, it does have a little bit of a change, but for the most part, we're going to be dealing with standard conditions. We're dealing with distilled water, so you can think of it as 4.18. Some places do 4.186. Not sure why the book or whoever wrote this curriculum a long time ago did 4.18, but I've stuck with it, and it's close enough. Some places will do 4.180. It just kind of depends on your initial conditions, I suppose, but we'll use 4.18 from here on out. Every material is going to have its own specific heat. So water is 4.18, but iron is going to be... Okay, let me not talk about this. Let me go here. It moved away. I'm sorry. Iron is 0.46. Your aluminum is 0.88. Lead is 0.13. So let me do something here I've never done before, but maybe I shouldn't because I'm kind of regretting trying something new already. Let's see here. Yeah, I can color iron. Oh, look at that. There we go. Let's do aluminum. Color. Look at me color. And then, let's do some lead because lead is cool. Is lead cool? No, not if you eat it. Don't eat lead. Okay, why did I do that? Well, because notice that these are all metals. Oh, let's make a key. Oh, we need a key. Yes, we need a key. Metals. And I like metal. Okay, so notice one thing about all your metals. They have very low specific heats. These are known as good conductors. Your metals are good conductors. A good conductor is not, basically they allow heat or electricity, energy or electricity to transfer through relatively easily. They have very low specific heats because it doesn't take a lot of energy to heat them up or cool them down. Then let's do some red highlighting. Your water, that's not red, that's yellow, you said. And I know, I'm aware of that. So we're going to change it to red. And there. That doesn't look too good, but it works. So your waters, your oils of the world, ice, alcohol. And there we go. Alcohol, all that good stuff. Going back to there. These are your insulators. And I'm not, I need to be black. There we go. These are your insulators. Your insulators generally take a lot of energy to heat up or cool down. Water is particularly a good insulator. A good example would be, let's say I want to boil some eggs because I'm hungry. All right, so I get out this big old, let's call it an iron pot, and I fill it with water. And after about, I don't know, 7 minutes, I touch the iron pot, it burns my hand. But if I touch the water, it doesn't burn me at all. That's because the iron just heats up so much better. It's a good conductor. And so it's able to heat up faster than the water. Even though both could be exposed to the exact same amount of energy, well, let's assume they are, it doesn't matter. The water is going to take longer to heat up just because it's got a higher specific heat. So it's a really good insulator. At the same point, it also resists temperature change in the other direction. For example, a lot of your waterlogged cities up in the north, Anchorage, for example, their wintertime temperatures are relatively mild. That's because they're surrounded by water, and it kind of helps regulate the temperature. I mean, there are places inland, such as Winnipeg, Canada, that I'm pretty sure are colder, or at least have colder days in the winter. And that's just, even though it's further south, and that's because of the water. It helps regulate the temperature. At the same time, the water helps keep the temperature down in the summer, so it's kind of it's like a buffer. The Inuit built igloos out of ice, or you build a snow cave if you're in a survival situation. And that's an insulator. When you don't think of yourself as it's an insulator, but well, let's just say it's negative 32 Fahrenheit outside, and you build that snow cave. Well, the walls are 32 degrees Fahrenheit. 32 degrees Fahrenheit is a lot more tolerable than negative 32 Fahrenheit, and it can keep out the wind. And so you can actually use ice as an insulator. Even though, I mean, it's cold to the touch, as long as you keep your body off the ground, this is how people have survived in survival situations. And then I threw in granite. I'm not sure why, but I guess I needed something odd. Granite's just kind of in the middle. I guess it's more of a conductor since it's closer to aluminum, but a lot of your rocks, this is one of the lower ones, a lot of your rocks are around 1 plus, somewhere in that region. So, anyways. Yeah, so conductors and insulators. So I should do a few practice problems before, just do a few practice problems. The heat capacity of a strange liquid is around 150 joules per degree Celsius. If the mass of the liquid is 50 grams, then what is the specific heat and how much energy does it take to heat the substance up 10 degrees Celsius? Okay, so a couple things I need to start off with. I know that my heat capacity is nothing more than my mass times my specific heat. So we haven't used mass before, so I'll put mass. We kind of have, but it's in grams. But I'll go ahead and put that in here. And C, as I mentioned earlier, is your specific heat. And that's in joules per gram degrees Celsius. K, okay, there you go. Okay. That is your heat capacity. Okay, well, we want to know the specific heat of whatever it is. Well, I know that K, the heat capacity is 150, and then I know my mass is 50, so then I could just plug it up here. Okay, 150 joules per degree Celsius is equal to 50 grams times C. We divide the 50 into 150, and notice that you're going to get 3 joules per gram degrees Celsius. So, an exceptionally small specific heat, but it's a strange liquid. Strange things happen. Okay. All right. Well, how much energy does it take to heat the substance up 10 degrees Celsius? And so I know, whether you know that or not, I'm now introducing it, and I usually call it delta E. is equal to K, try it one more time, K delta T. You might see this written in chemistry classes as a Q is equal to, say, K delta T. I will generally use delta E just because that's how it was set up, but if you want to use Q, that's fine. Q equals MC delta T is the formula I still remember from high school chemistry, but Anywho, I want to know energy because, well, it's what I want to know. Well, we're going to find out. I take my 150 joules per degree Celsius, and then I multiply that by my 10 degrees Celsius. Notice your degrees Celsius cancels, and you get 1,500 joules of energy. So it takes 1,500 joules of energy to heat the substance up 10 degrees Celsius, or it would take 1,500 joules of energy to it would take the removal of 1,500 joules of energy to drop the temperature of the substance 10 degrees Celsius. Excuse me. All right. You use a coil of water to heat 100 grams of water for 5 minutes. Its temperature changes 45 degrees Celsius. Then you use the same coil to heat another sample of water for 8 minutes, and its temperature changes 30. How much water is in the second sample? Okay, so so you're using a power supply. So you're doing two situations. You have power 1, and you're going to have, I guess this is a comma. You can see that. Power 2. Power 1, power 2. We use the same coil of wire. We use the same power supplies. And so what we know is that power 1 is going to be need to equal to power 2. They're going to put out the same amount of energy per unit time. What's different is the time. Notice that this time is 8 minutes and this time is 5 minutes. So that's going to differ. Well, power is equal to the change in energy over the change in time. And so what I want to do is plug that in here. So that gives me, well, I need a better one here. All right, here we go. Delta E1 over delta T1 equals delta E2 over delta T2. All right, we're getting a little bit better here. Okay, so they give us a mass. The fact that they give me a mass means I may not be able to use heat capacity. And so running up here, kind of jumping ahead a little bit, we know that K is equal to MC and delta E is equal to K delta T. Therefore, delta E is equal to MC delta T. Yes, MC delta T. Kind of sounds like a rapper. Well, an old rapper, like MC Hammer. So, a 90s rapper, MC delta T. So, anyways. Well, okay, so I know MC delta T, so I'm going to make that substitution over here. All right, so we have M1, oopsie. M1 C delta, and I make sure it's a capital because we have two different ones here. Delta T1 over little delta T1 is equal to M2C delta T2 over little delta T2. Okay, so you notice that I put C, and I left the C the same. I didn't put subscripts. That's because we have water and water. Since water is the same on both sides, I can cancel my C's. If I cancel the C, that's going to make my life a lot easier. That reduces this little puppy to M1 delta T1 over little delta T1 equals M2 delta T2 over little delta T2. And I need to extend that. Okay, so, all right, now I can plug in what I know. All right, we got 100 grams of water. Delta T1 is 45 degrees Celsius because that's the temperature change over the time. Now, normally we would need to convert minutes to seconds. You don't in this case. I will show you why. If you want to do it to be on the safe side, by all means you do that. But you don't need to, and I'll show you why. So 100 grams, 45 degrees Celsius, 5 minutes. Then I have, I don't know the mass, so M2. The temperature change is going to be 30 degrees Celsius, and then that's all over 8 minutes. Now, the reason why I didn't convert to second is because I just knew, since they're both in the denominator, that the minutes were going to cancel. Sure, I could have put 5 times 6 is 300 seconds and 480 seconds here, but seconds would still cancel. This makes it a little bit easier mathematical-wise. So, let's do some simplification. Well, my calculator has a low battery. Stop. There we go. It stopped. Good. I needed it to stop. 100 times 45 times 8 is going to give me 36,000. So it's going to give me 36,000. That'll be grams per degree gram degree Celsius. Minutes is already canceled. And on the other side, we're going to get 5 times 30. It's going to be 150 degrees Celsius times M2. That's a really bad... Oh, I'm tearing up myself. Okay, here we go. M2. There we go, it's better. Notice that your degrees Celsius cancels. That leaves you with grams. That's the unit that you wanted to begin with. And if you're saying to yourself, why the hell did he just write 3,600? Well, that's because he meant to write 36,000. But he caught it. He did catch it. So, we're going to divide it by 150, and I get 240 grams is equal to the second mass. So, it's a different mass, and it should be. It's higher than the original 100, but it should be. Why is that? Well, it was heated up for longer and had a smaller temperature change. That tells me you're going to need more of it in order to, if it's going to take longer, it's going to need more of it. Then, if you're going to have a lower temperature change, it's going to be even higher than that in order to at least be equitable. So, anyhow, you will have a problem like this on your homework. Do reference this when you do your homework. Do note a few things. These specific heats are the same. I think they are the same when I give it to you on your homework. If they're not, well, the C's don't cancel. So be careful on that. And as always, if you have any questions, please email me. And that should be it for this lecture.